Okay, so page 19. No, Diane, turn off the lights. Loris, do you think you can reach the switch to the front one? Yeah, thank you very much. And so let's do a little bit of a timeout here. What have we done so far? So we started off with just the basic fundamental counting principle, right? Which we figured out the number of ways something can be done, right? So we would take event 1, so let's say it's tossing a coin, we would multiply that by event 2, let's say it's rolling a die, right, or dice, and then this would continue on, right, for as many options as we were given. Or let's say we have, 3 colored shirts, 2 colored shorts, and some socks, right? We would do it this way. Or we would have, what is it, pizza, right? So many crusts, this many toppings, and so forth, right? You had options there. So that's what we started off doing. It's like, how many ways are there to come up with that answer, right? Number of ways to do something. So we started off that, and then we moved on to what I would call passwords, right? Passwords and numbers that can be created, and that was a little different because there, you filled in slots. So let's say you had numbers 0 to 9 available, you can repeat, right? So it's 10 times 10. So every event basically has the same number of outcomes, unlike this first section that we did where every event probably had different outcomes. And so this just repeated. So what you ended up noticing is like, hey, I have n number of options. I just have to take that to the power of, and we talked about R. Yesterday we talked about R, NPR, right? N is the number of options that you have available. R is how many are you grabbing at a time, right? So we kind of had this. So in this case, it would be 10 to the power of 3, right? Where 10 is the options available, 3 is how many events are happening. Okay, that's what we did next. And then we talked about a factorial, right? Factorials. And when you're dealing with factorials, right? What's happening there? What is the question implying when it's factorials? That you have a limited supply, right? That the number of options is going down, right? So, instead of 10, 10, 10, it'll be 10, 9, 8. And we did talk about that here already, right? I did throw questions like some restrictions. Hey, you can't repeat. You only have this many. But then we said, hey, there's an easier way of writing it, right? Factorials. Like, for example, if you saw something like this, what factorial notation would you use? Using permutations, you would have to realize, oh, how many are in the bag, so to speak? There are 10 options. And how many am I picking in this case? I pick 3, right? So this is a quicker way of saying that exact same thing. So we're still, when you ever have slots like this, you're using the fundamental counting principle. And then, right, you can state it as a power, you can state it as permutation like this, okay? And then what else did we do? We realized that sometimes we had cases, right? Cases is when there's an overlap. You would probably have to focus on the word or, right? Something can start with a B or an L, right? And then you would have to break it down into cases. What if this happens? What if that happens, right? And then, so if it's a password, a license plate, whatever you're doing, right, you would have to do that multiple times and then later on add them up to come up with your final answer, right? That's what we did as well, okay? We also solved for factorial equations, right? I'm just making this up. I don't know if this works out, but we did solve for this, so that's another thing we did, right? And then yesterday, what did we start talking about yesterday? Do you remember grouping? Did you do some of that work? I hope so. But in a sense, I gave you a formula, right? Which I will just show you. But basically, you take G1 factorial, G2 factorial. So however many groups there are, right? So let's say there are groups of 3, groups of 5, whatever. This pattern continues, right, until you get to the group K, let's say, right? Like this, how many groups there are. And then at the end, sorry, everything has a factorial, right? So as many groups as show up, but then at the end, this is the important bracket where you would take your total and you would subtract, hey, how many were in group 1? How many were there in group 2? And you would continue this till you get to GK, plus you would have to add the number of groups that are involved at the end to make this correct. Okay, so we're going to do a couple more of those today, and I will show you various other things that I kind of need to just fill in the gap as we go along. We know more and more. I can kind of mix things up a little bit. Okay, so this is just a little overview. I will give you a better map later on when we've done everything. I will give you a map, right? So we'll do that at the very front of this booklet, kind of like going all over the place, and it's going to be a little cleaner to fill in. So let's, anyways, this formula should be on your study sheet. Some of you probably already have it, but very important to have this in your study sheet, okay? So let's go to the next page there. And I will try to use my iPad for this one, just to show you when you're grouping things together, how does that work? Just gonna get rid of that. Right, so anyways, so if you have, let's say, people, right, being arranged like this, and let's, for example, just say we have 5 people that are arranged in a row, right? And all of a sudden you're like, hey, I want 2 people to be together all the time, okay? So then we would group them together. So let's say these 2 are staying together. Let's see if this works. There you go. Yeah, works pretty good. So they always have to stay together, right? So this would be one permutation. Let's see here. Is there a clone somewhere? We'll just copy and paste here. So let's say my second permutation, right? This group that used to be here is now here, right? So they're moving together along this arrangement, and this would go on for as many times as is needed, right? So the first thing you need to do is you need to take this group, right? That would be your 2 factorial. That'd be your 2 factorial, because these individuals within the group can switch, right? This, like if you want to look at it, that would be times 2 times 1, right? 2, 1, because they can switch. But then they need to stay together within the group. These are always together. So in this case, there's only one group. So you'd say a total of 5, that's how many individuals are in this case present. You would subtract the 2, right, in that group. And then what would I have to add in this case? The number of groups present. In this case, it's just 1, actually. The number of groups, the formula does say that. The number of groups present, right? So look in the front here, how many groups do you have? In this case, there's only 1 group, so you'd have to add 1 and then factorial that. So that gives you what? 2 factorial, 5 minus 2 is 3, plus 1 is 4, 4 factorial. And you're like, why is that? Well, think about it. If you think about this grouping counts as a big slot, right? That is filled because these stay together. So 1, 2, 3, 4, right? when you look at the outside, when you zoom out, there's really four slots to be filled. So it's almost like 4, 3, 2, 1, right? But then within this group that is supposed to stay together, you can switch them, and that's where the 2 factorial comes in, right? So this part is fulfilled by that, and the big picture here is fulfilled by that. Okay. Cool, huh? Right? I think so. So let's say this gets more complicated. You're making groups, and there's more and more students in your groups. Like, I want to be with so and so, right? So let's make that. Let's switch this up. Let's see if this works. Can I circle and tap? No. That's my smart board used to be like that, but not anymore. And I'm apparently also erasing the smiley faces. That's okay. Okay, so let's say things get more complicated. These are together, and those 2 have to stay together. So if we just, before we even use the formula, let's just do this. How many slots are there when you zoom out? 1, 2, 3, right? These 3 can be arranged. So that's where the 3 factorial at the end comes from. And so group 1, this is kind of like group 1, and this is group 2. So that'd be 2 factorial times 2 factorial times 3 factorial. That's like the big picture here. Okay. How would this work using my formula? I would say, hey, there's a group of 2. There's another group of 2. And then I need to take the total, which is 5, subtract the number of individuals in the first group, subtract the number of individuals in the second group, and what would I have to add here? How many groups are there? 2, yes. And I hope this works out, right? 2 factorial, 2 factorial. 5 minus 2 is 1, right? Plus 2 is 3. Exactly what you got up here. We're getting that again here. Okay. So I'm going to do a couple of examples today, more grouping kind of scenario. And unfortunately, my booklet, my second part, is not here yet. So you're going to have to write a few things down. I'm pretty sure it's going to be here Monday. I hope so. But I'm a little bit behind with that. They're 5 days behind, right? So yeah, apparently there's a shortage of paper. That's what they're telling me. So let's go to page 20 here and do more grouping. And I need to change the numbers here because these numbers are very, very big. So everything would be in scientific notation if we kept those numbers. So let me see, where's my draft here? I went over it yesterday. Somebody steal my draft? Oh, here it is. Who would steal my draft, right? Who cares? Anyways, I changed this to 5 and 4. 5 and 4, right? Yeah. Change that to 5 and 4. Okay. It's 5 girls, 4 boys in a class. How many ways can they be seated if there would be no restrictions? So obviously, just follow me for now because I want you to see that everything is connected, right? Using the fundamental counting principle, we have 9 seats. Okay, 9. By the way, have you noticed that everything we arrange is in a line? Have you noticed that? It's always in a line. You could arrange something in a circle. I'm going to do that at the end. Okay, circles. There's a bit of a little trick to it, but it changes things slightly. So this would be 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? So that would be fundamental counting principle. This is fundamental counting principle. And then we could also write it as just 9 factorial. That would probably be the easiest, right? Or we could also write it as, using permutation, you have 9 students, you pick 9. Okay. All of these are, this is factorial. This is permutation. They're all saying the exact same thing. So you want to use your calculator, come up with 9 factorial. Let's just do it because it's the time, right? It takes time to type everything in. And you need to remember where to find the factorial, right? Math, go get it. And this is 362,880 ways. Can I have a confirmation on that? Is that what we're getting? Yeah? Okay. And so P9, 9P9 is the same thing as this, same thing as that. So that's just 362,880 ways that these students could be arranged. So there's no restriction whatsoever. That just means sit wherever you want. Okay. And would we would agree, right, that all individuals are distinguishable. There are no identical twins in this story, right? I've had identical twins in my applied classes, and that was a hard year for me to distinguish. So what about if all the girls sit together? So 5. So what is that? That should be key for grouping. Okay, we have a grouping situation here. So we notice that, right? That would be a group of 5. So within that group, we can have 5 factorial, correct? And on the outside, we would go total, which is what? 9, right? Total minus the number of individuals in that group plus how many groups are present in this scenario? Just one group, right? One group. How about I do that in your notes? I will actually do that, hey? That is a good, to tell you, where did I get this from? It's like, oh, there's one group. That's why I went plus 1. So then we go and clean this up a bit. This would be 5 factorial. 9 minus 5 is 4, plus 1 is 5. Coincidentally, 5 times 5, that's what it is. You know what I've started to do? I started to just memorize some of the factorials. And here, I'll just give them to you up top here. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2, right? So 1, 1, 2. 3 factorial is 6. 4 factorial, it's just 4 times 6 basically, right? 24. 5 factorial is 120. And I ran out of room. 6 factorial is 720. So I don't know, like having the first 6 on your study sheet, maybe it's going to save you a lot of time, right? So anyways, 5 factorial and 5 factorial is really, let's go here, 120 times 120. And that is 14,400 ways. Can I just, this is technically some sort of restriction, right? Grouping counts as, it is a restriction, right? We just didn't look at it before. And so now, boys sit together. So there'll be 4 factorial. 9 minus 4 plus 1 group. Factorial, so that'll be 4 factorial. 9 minus 4 is 5, plus 1 is 6. So that is 24 times 120. No, 720. That's 17,280 ways that you can arrange. Oops, this away. So slightly more ways, right? Slightly more ways. And why is that? Well, because you have technically, right, the 6, you have more options now to shuffle, right? The group that needs to stay together is smaller, but you can shuffle everything. So there's a few more. So the difference, there's a bit of a difference there, right? How about this? Girls sit together, boys sit together. Okay, so group 1, group 2. 2 groups. So no problem. Bring it, Mr. Dirksen, just bring it. You can give me 10 groups if you want. I know what to do now, right? Group 1, group 2. Then I open my brackets. I go 9 minus 5, right? The number of individuals in the first. So basically, take away the numbers you put in front of the bracket. And then you go plus, how many groups? Those, right? Factorial. Don't forget the factorial. That is a classic mistake. Let's change that. Okay, so you have 120 times 24 times 2, which is really 48 times 120, right? You better follow, right? You better follow with your calculators because, you know, my track record is not the greatest. Good thing you're graduating and then you're gone next year. I don't have to face you in the hall anymore. I'm just kidding. I'd like you to stick around, but it's much better being out of high school, trust me. So there's that, right? Fewer ways because now you have 2 groups that need to stay together, right? So you can't really do much in the greater picture when you zoom out. Is this making sense on a Friday morning? You don't seem as excited as I am. That's okay. That's okay. Why would you, right? Mr. Dirksen, I just sit down. I don't worry how many ways. Just leave me alone. Okay? Girls sit together. Girls sit together. That's a group. Group 1. John and Carlos sit beside each other. So that's a sneaky way of, right, another group introduced into the mix. Right? So, and I'm going to add here, guys. That's why there's blank. Because at the time, that's all I had. But then the more I think about it, the more I add. Basically, what I do is I do the homework. And then I come back and edit. It's like, oh, yeah, they probably need a bit more to do the homework. So if you're doing your homework, you should be well prepared. So girls sit together. There's 5. John and Carlos, that's just 2. So 9 minus 5 minus 2 plus 2 groups. Factorial that one. 5 factorial, 2 factorial. So 9 minus 5 minus, that's 2 plus 2 is 4. And hold on. So this is John Carlos. Group 1, group 2. Total 5, 2. Add the number of groups. Go ahead. So this is what, 120 times 2 times 24. So 48 times 120. It's the same as before. Same as before, because I can just, right? That's okay. It happens. It happens. It's okay, dear. Do what you must. Okay, F. Here's a little twist. Watch this. I will do this one. What if I did this to you? What if I said do not? Do you remember n of g naught? Do you remember that from set theory? What would you do to get naught? You take the universal minus n of g. What is my universal in this case? If you had to go A, B, C, D, E, what's the universal in this case? Hint, hint. If you just sit down, right? Like you forgot, this is really all you could do. Like if you went all out and rearranged everything, there's not 362,880 distinct arrangements, right? So this is your universal. Universal set, so to speak. So you had 9. So when it comes to arrangements, this is your universal, no restrictions. Okay, so let's see what we can do here. So this is going to be my approach. I'm going to go total or universal, okay? And I'm going to subtract, right, girls sitting together. Does that make sense what I'm doing here? Well, you know what this is called? This is called indirect reasoning. Not direct reasoning, it's called indirect. Because you're going to just worry about taking away the cases where that is the case, and you're left with all the cases where that's not the case. So universal is 9 factorial. Let's just do that. 9 factorial minus girls sitting together would be, let's just do that here. That'd be 5 factorial times total minus 5. Because this could be a separate question, right? This could have been a separate question. So I'll just go through the whole thing. Minus 5 plus 1 factorial. So that's 9 factorial minus 5 factorial. And this is 5, right? So that is essentially how you would get there. Okay. So 9 factorial. Oh, why again? Why again? That's 362,880 minus, I will just go and get it from up there. That was B, right? 14,400. It's 348,480 ways. Indirect reasoning. More to come. More of this to come. You will see me do that more and more. What about John and Carlos are not to sit together because they always chat, right? They're always distracting each other. Don't want that to happen, right? You do the same thing, except for this part would be all the cases where they are sitting together. And right, so just slight variation there. This is grouping in a nutshell, guys. Grouping, done, right? If you want more grouping in the textbook, that's where you find it. Look at my time very carefully here. So let's go to the next part, which is dealing with identical objects. What if things are exactly the same? Like, what if there's 2 of the same? So for this, I'm going to ask you to go to page, there's a blank page here somewhere. I think it's page 17. Yeah, 17, extras. So I'm going to give you a bit of a crash course today. And then on Monday, when we get our booklets, fingers crossed, that's when I'm going to kind of just use the nice layout that I have in the booklet to do more, okay? So extras. So where's my... Let me get my iPad first here. Or maybe I'll just start with some notes. So we'll call this 4.4 way at the top. Okay, don't use up too much space. 4.4. This is permutations involving page 17. Okay, identical. What happened there? Objects. Okay. To avoid double counting, we need to divide out permutations. Time out, Mr. Jackson, I don't like that word. Almost sound, it looks like a swear word to me. Permutations is just another way of saying ways of arranging, okay? Permutations is just arrangements, right? You can say divide out arrangements if you like in your head, put that in, but you're going to see permutations a lot moving forward. So divide out arrangements that involve identical objects. Okay, so for example, let's use the word applied. How many ways can letters in the word applied, nice and capital, be arranged? How many ways could the letters in the word applied be arranged? And so you've done this before. You did pre-cal, right? The word pre-cal, how many ways can you arrange that? Any word that can throw at you, you should be able to do it. But what's different here? What's up here? Do you notice something? There are two P's. So technically, let's call this P1 and P sub 2 to distinguish them just for ourselves, right? If you want to do another one, let's flip P1 and P2. Okay, let's flip that. Let's just focus in on these repeats here. To the naked eye, right, they're the exact same. This permutation is exactly the same as this permutation, right? It's not distinct. These are not two distinct permutations. So we will say this, right? Same arrangement. Okay. So we'll do this. What you do is you count the number of letters. N is equal to 7, correct? And you have two P's. Two P's. Okay? So you would normally just say, hey, that's 7 factorial. But now you're going to divide out the number of repeated elements. This could be marbles, right? Red marbles, let's say. This could be coins. They're non-distinguishable. So you get really 7 factorial is 5,040 divided by 2, which is really 20 ways, right, that the letters can be arranged. So this, maybe make an arrow go to that, right? So you need to divide out when you see that there are identical objects, right? How about this? Identical objects. These are your identical objects here, and we divided them out, right? It really sticks out. What about Mississippi? That's a classic, by the way, guys. If you YouTube permutations involving identical objects, Mississippi is almost guaranteed going to be one of the classic ones for this particular problem. So first of all, you need to remember that the word applied, right? If those letters are being arranged, there's a limited supply. First of all, same here. You don't have an unlimited, right? That's why we're using factorial. So Mississippi is the word. So let's figure out how many letters are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters. Okay, and you should immediately figure out how many S's are there. There are 4 S's. There are 4 I's. Am I missing something? Yeah, 2 P's. Okay. So lots of repetition, right? Lots of repetition. So there's a number of permutations that we would not want to include in our calculation, right? So basically, you would go 11 factorial, right? There are 11 letters. And this is going to have a longer line because I have 4 factorial, 4 factorial, 2 factorial. I'm dividing out, and this is where your highlighter, if you have 3 different highlighters, today is the highlight of, that's the highlight of Friday, guys. Boom, boom. My goal is to convert at least half of the class by the end of the course to go highlighter. Okay? Okay, so there are your, and by the way, guys, I don't know, I haven't seen this mistake yet, but it happens. Some students say, hey, 4 and 4 factorial, that's just 16 factorial. That's wrong. That's going to be very wrong. Your calculator is not going to be able to handle it, right? So just make sure you don't do that. So that'd be, I've got 11 factorial figured out already here. So 39916800 divided by 24 times 24 times 2, right? And so you need to, the reason why I'm doing this in steps is I will first figure that out, and then you do this separately, come up with a number, and that's 1152 if you multiply this out. That seems very small. Yeah, no, we're good, Yeah, we're good. So then this divided by that, you get 34,650 arrangements. Can I just say something about identical? I don't have to tell you this. This I don't have to tell you. Grouping, I need to tell you what's grouped. This, I do not have to tell you this. I can just say, hey, how many ways can the letters in the word applied be arranged? And you need to know this. You need to recognize, oh, repeats, right? And so, can we do this? What if, let's make this a B. What if all I's are grouped? Let's add the layer. What if all the I's need to stay together? You don't have an option. The I's have to stay together. And you're like, isn't grouping something different? Yeah, but we can combine them. We can. So all you need to do is take care of the grouping and then take care of the repeats as well. So we're going to go, how many I's are there? 4 I's, right? Based on this. So basically you start with that. Group number 1, this is group 1, right? There's only one group. So 4 factorial times 11 minus 4, and you've created one group, factorial. Then slap those, you got to get rid of those repeats. You still got to do that, okay? So I'm going to highlight again. So this is my, that, and this, okay? And then let's clean it up a bit. 4 factorial, this is 8 factorial over 4 factorial, 4 factorial, 2 factorial. Can we cancel these two? Yep, boom, gone, right? Let's do a little bit of simplifying here. These two can go. So really just 8 times 7 times 6 times 5 divided by 2, right? This one I need to, so that's 30, 210 times 8, 1680 divided by 2. So that's 840 ways. Okay. So grouping meets identical objects, right? Okay. That's all I'm going to do for this. So if you want textbook homework, page 266, 1 to 7, and comma, 15 to 17. So write this down. Try a few. You will have coin examples. You will have true and false types of scenarios and so forth. So you got to just give it a try, okay? And one last thing before I get you to do your own, to work a little bit. I want you to go to, there's a bit of a page 16. One last thing, page 16. I'm just going to review a type of factorial equation that you might encounter. Just a little twist to it. I want you to be able to do it if you come across it. Okay? So page 16, this, I don't know if you did that. I gave you the answers there. So wherever you ended up with your work, make a line like that. Okay? Wherever you ended up, if you want to give yourselves room to do that later, go for it. But what if I give you something like this? What if I said, hey, solve that one, solve that one? At first glance, you're like, what do you mean, solve that one? Well, let's remember at the top here, NPR is whatever this is, factorial, over this minus that, right? Factorial. That is the formula for permutation. Okay. So can I just use highlighters again? That whatever that is factorial, and whatever, right, the subtraction I will leave. I will not touch that one, but just the whatever n is factorial. So you almost, the question usually won't have a bracket, but you can almost consider this the thing that you're gonna factorial right off the top. Okay. So watch what I'm gonna do. I'm gonna, on this side, on the left side, I'm gonna use this formula right here. You're following? So this, right, whatever that is, needs to be at the top. So we're gonna go n minus 1 factorial, right? Just like we did on the original there. Okay. And then what goes at the bottom? It's the first minus, watch this, it's n minus r. In this case, this is like your n. Okay, so it comes back here. N minus r. R happens to be 2. All of that factorial. And then remember that on the right-hand side, you still have the 31. Does that make sense, guys? I'm taking whatever is here and factorial it because that's what the formula says. Whatever is here goes in the numerator and you factorial that. In the denominator, you subtract these two and then slap a factorial to it. So I'm going n minus 1, which is this. Subtract, this is like a big subtract, right? Whatever is here. And let's clean that up a little bit. N minus 1 factorial over, what's this? N minus 1 minus 2. That's really n minus 3 factorial. All of that is equal to 31. Hold it, restrictions, right? At this point, you do restrictions. So n has to be greater than or equal to 1. N has to be greater than or equal to 3. This is the greater one. That's the overall restriction. So that's what must happen. That's the least that you need to abide by to make this work. Which one of these two is the bigger expression? The top, right? N minus 1, right? So we're going to expand that. N minus 1 times N minus 2 times n minus 3. Remember, whatever you start with, it's going to drop by 1 every time. You're going to factorial that because you know that in the denominator, you have the same thing. And remember, the 31 is still there. So there we cancel this out. So it's n minus 1 times n minus 2 is equal to 31. FOIL it, n squared minus 2n minus 1n plus 2. That is equal to 31. And now you just, because it's a quadratic, you bring everything over to the left or to the right, whatever you want to do, but you have to have equals 0 on one side. N squared minus 3n plus 2 minus 31 is equal to 0. Hold it. I made a mistake on my original. This is 30, guys. Oops. Otherwise, you get a decimal, and you cannot have that. My bad. Easy fix, though, right? Easy fix. That's what I get for making up questions, right? Serves you right, Mr. Durson. Minus 3n plus 2 minus, that's minus 28. And here you can use your calculator, right? If you want, this goes into y1, this goes into y2, and then goes second, trace 5 to determine the intersections. Do you know how to do that? Go ahead and do it. Some of you like to factor. Go for it. Just factor it. Okay, graph it. There it is. That's all you need to see the x-intercepts. I'm going to go to the left. Enter, enter, enter. That's negative 4. N is equal to negative 4. And the other one is going to be my winner. Enter, enter, enter. That's 7. N is equal to 7, sorry. So this is this does not work, right? It does not abide because this one tells me that n is greater than or equal to 3. That's why that checks out, right? And encourage you to plug that in, right, just to do your check. You know what? You can actually go all the way up here. Just plug it in here and see if that works, right? Because it's really n minus, so it's 7 minus 1 p2 is that equal to 30. That's 6p2 is equal to 30. And we all know what's 6p2 again? 6 times 5, remember? You're picking 2, so it's 6 times 5, which is 30. 30 is equal to 30. Checks out. Right? So if you ever get something like this, you just have to use this formula, set this up, plug these things into this formula, and then it's basically the same as before. Okay, I'm stopping there. What I'm going to give you is not an AC, but just a review of things that we've done here. I just want to, oh yeah, this one, with identical objects. Looks like this.